Good morning to all of you. Today we are going to discuss the post-processing aspects of ceramic matrix composites. But before we start our discussion on the post-processing aspects of ceramic matrix composites, let us first see that what we have already covered in this particular module, because this is the last discussion or last lecture in this particular module on ceramic matrix composites. So in this particular module, our focus was primarily to discuss the details about the ceramic matrix composites with a focus on the processing aspects of ceramic matrix composite. So in the very beginning, we have seen that what is the difference between the ceramics and the ceramic matrix composites, why do we need to reinforce the ceramics, what are the disadvantages of the ceramics which can be overcome by reinforcing them with the reinforcement phase. Then we have seen that what are the various types of toughening mechanisms that are prevalent in case of ceramic matrix composite, and then we focused our discussion on the processing aspects of ceramic matrix composites. So basically, whenever the word composite comes into picture, all of us know that there are two macro constituents that combine together to make a composite material. Now these two macro constituents are the reinforcement and the matrix. So we have to somehow combine the two things together, that is the reinforcement and the matrix, to make a composite material. We have already seen in the previous module that how the polymer matrix composites can be made, and we have seen the processing aspects of polymer matrix composites with the help of number of processes such as resin transfer, molding, filament winding, pultrusion, and a number of other processes. Similarly, in case of ceramic matrix composites also we have seen a number of processes till date. If you remember, in our previous lectures we have seen the powder processing method for processing of ceramic matrix composites, then we have seen chemical vapor infiltration, we have seen slurry impregnation, liquid infiltration, and today our focus would be on the directed metal oxidation process, and finally we will see the post processing aspects of ceramic matrix composites. So basically, if we see the processes that we have already covered in ceramic matrix composite, the reinforcement phase is mostly, or maybe in all the cases, has been in the solid form only. Starting from the powder processing, we have seen that powders of the reinforcement and the matrix are combined together, they are blended together, and finally pressure and temperature may be used to make a composite product. In case of CVI also we have used a preform and then the infiltration or the impregnation of the vapors, gaseous reactants into the preform. And then in liquid infiltration also we have seen that we have a fibrous or a network of fibers forming a preform in which the liquid infiltrates. So in most of the cases we have seen that the reinforcement is in the solid form and the matrix is somehow generated into the preform or created inside the preform, so that we get a complete structure which is a composite structure in which we have a reinforcement phase and we have a matrix phase. So basically the focus is on combining the two things together, and in our discussion on ceramic matrix composites also we have seen that the reinforcement and the matrix have been combined together in a number of ways, like powder processing, chemical vapor infiltration, slurry impregnation, liquid infiltration, and there can be other processes also, but these are the important processes that we have discussed. So today our focus primarily would be on two processes, just the basic fundamentals of the process, that how the process actually takes place, and finally we will conclude this particular module with a discussion on the post processing aspects of ceramic matrix composites. So with this introduction, let us now start our discussion on the basic aspects or the basic fundamentals of the directed metal oxidation process. We will first see the salient points in the form of an introduction to the process, and then we will try to understand the process with the help of a diagram, and finally we will see that what are the salient advantages and disadvantages of the process along with the applications of the process. So let us start our discussion for directed metal oxidation. So directed metal oxidation, basically we can see that the three words are there: directed, metal and oxidation. So directed means that in a particular direction the reaction would take place. The reaction would be for a metal because the metal word is coming in the name, and oxidation means the type of the reaction would be the oxidation reaction. For example, the aluminum may combine with air to form aluminum oxide. So directed metal oxidation means the direction of the reaction, the metal would be there and it would react and it would oxidize to create a reaction product. So this is the basic fundamental definition of the process, that is directed metal and oxidation. So we can now have an idea that what is going to be there in the process, that there is going to be a reaction that would take place and the products of the reaction would be used either as the reinforcement or as the matrix. But as the history goes, or as we have seen in the previous processes that we have already discussed, the matrix is being created or being generated or being formed inside the fibrous preform. So the reinforcement in most of the cases is already in place, but the matrix has been, we can say in a very simple terms, grown into the preform to make a composite material. So in this case also our focus would be on creating the matrix only, and the reinforcement would be in the form of a preform only, which would be created before the reaction taking place. So we would be seeing that what are the various steps involved in the directed metal oxidation. Let us see the introduction of the process. In this we will see the various steps involved in the process. So in the very first step, a preform is prepared. As we have seen in the other processes for processing of ceramic matrix composite, the preform is a prime prerequisite for making a composite material. So the preform is created. In most of the cases we have seen the preform is made up of fibers. Sometimes particles can be used for making a preform, or whiskers can also be used. So the preform is basically the reinforcement that is going into the matrix, or that is being combined with the matrix to make a composite material. So first and foremost we have to generate a network of fibers. It can be continuous fiber or discontinuous fiber or whiskers, which can be used as the reinforcing material inside the ceramic matrix. So first and foremost job is to create a preform, that is first and foremost job is to bring the reinforcement into the picture, and finally we will bring the matrix also into the picture. The reinforcement and the matrix would combine together to make a composite material, and more specifically a ceramic matrix composite material, because this particular module is focusing on the ceramic matrix composites. So therefore the matrix that would be generated would be a ceramic matrix. The fibers also in many cases would be ceramic. So therefore we will get ceramic composite material, in which the reinforcement is also a ceramic material and the matrix is also a ceramic material. So the very first step in case of directed metal oxidation is to create a preform. So in the very first step the preform is prepared. How it is prepared, that we will try to see with the help of a diagram. In case of particulate composites, the preform can be a ceramic green body. Ceramic green body means there can be, because the particles are there in the form of reinforcement, green body means that there would be other additives also. So it would be a green body means it would have a structure, it would have a form in which the ceramic particles will also be there and would be binded together with other additives. So it is also important to note, because if the reinforcement is particulate, the green body or the preform would be different, and if it is a continuous fiber reinforcement, the we can say preform would be of different shape and form. So basically we can see this particular point clarifies that the particulate reinforcement can also be used in directed metal oxidation. So in case of a particulate composite, the preform can be in the form of a ceramic green body. But for the fibrous composites, in which we may be having a continuous fiber, the preform is prepared by filament winding or fabric layup process. So this is emphasizing the creation of a preform, or this particular point is highlighting the creation or fabrication or processing of a preform before the processing of a ceramic matrix composite. So when we are preparing a preform, there are 2-3 important points that have to be taken into account. First and foremost, we have to see the reinforcement, the form in which the reinforcement is being used. If it is in the form of the particles, then we have to prepare a ceramic green body. If it is in the form of a long fibers, then we can use the filament winding process or the fabric layup process. So we can have a continuous preform, we can have a particulate type of reinforcement in the form of a ceramic green body. So first and foremost focus is on the creation of a preform, because in all of the processes that we have seen for composite materials, the focus has been on two important aspects, and these aspects are the reinforcement and the matrix. So right now in this particular slide, our focus is on the reinforcement part of the composite material, because here we are seeing that how the reinforcement has to be prepared for being blended into a matrix material. So we can see that the preform is prepared in the form of a particles also, or in the form of a continuous fiber reinforcement, which can be made with the help of two processes. The continuous fibers can be filament wound, or they can be made using the fabric layup process. So this is the first important slide related to the reinforcement aspect in the directed metal oxidation, and then slowly we will move towards the matrix aspect in case of directed metal oxidation. So on your screen you can see a barrier is placed on the preform surfaces to stop the growth of the matrix material. So here also we have prepared a preform, and in this particular preform the matrix would grow, and how the matrix would grow, that we would be seeing with the help of a diagram, but there would be a covering or a barrier that would be placed on top of the preform, so that to restrict the growth of the matrix material. So I am again reading the point on your screen to make it even more clear that a barrier is placed on the preform. The preform we have already generated in the form of a ceramic green body or in the form of a continuous fibrous preform with the help of filament winding or fabric layup process. So this preform is already ready with us. Now we are growing the matrix inside the preform, and for that a barrier is placed on top of the preform. Why a barrier is placed? So that the matrix can grow up to a particular level only. Before going to the next point, let us first revise this particular point, because this is also important. A barrier has to be placed on top of the preform. So a barrier is placed on the preform surfaces to stop the growth of the matrix material. So next point is the molten metal is subjected to directed oxidation. So as I have told in the very beginning, in the start of the lecture itself, that the name of the process is directed metal oxidation. So here we can see the molten metal, the metal part is coming into picture. We have already prepared a preform. Now the metal part is coming into picture. The molten metal is subjected to directed oxidation. So the other two words are also coming into picture, that is the directed and the oxidation. So the name of the process, directed metal oxidation. So the molten metal is subjected to directed oxidation, which results in the formation of desired reaction products on the surface of the molten metal, which grows outward. So we will try to understand this. We will have a preform, and below that we will have the molten metal, which would be subjected to the directed oxidation, and the products or the reaction products that would be formed on the surface of the molten metal would be allowed to grow outward. So when they will grow outward, they will enter into the preform and will form the matrix on the surface of the reinforcement. The reinforcements can be in the top form of fibers or the particles, and we will get a composite material. So we have a preform, we have a molten metal, and it is subjected to directed oxidation. The reaction products that are forming on the molten metal would be allowed to develop or move outward, and they will form the they will form the matrix inside the preform. So preform is already acting as the reinforcement. We have to generate the matrix. The matrix is being generated by the directed metal oxidation. That is the basic fundamental of the process. Now let us see some other points related to the process, and we will try to understand these points with the help of a diagram. On your screen you can see, first and foremost is the preform fabrication. As we have seen in the previous slide, we have to make a preform. This is the preform. We can see this is the preform. Now the next point is the growth barrier. This can be the white line acts as the growth barrier. We have a molten metal which is subjected to the directed oxidation, and the reaction products will form the matrix material. So this is the molten metal. the matrix growth is taking place. Matrix growth takes place in this direction. From the bottom, the matrix will grow into the preform, and finally when the whole preform becomes dense with the growth of the matrix inside the preform, we get a final product, that is a ceramic matrix composite. So again we can understand the process. This is the directed metal oxidation process. Very basic steps are given here. This is a reinforcement in the form of a preform. As we have already seen, the preform can have a particulate reinforcement, or it can have a continuous fiber reinforcement in the form of different layers of fabrics, or we can make it by a filament winding process. So we can have continuous fiber reinforcement, or we can have particulate reinforcement. If it is a particulate reinforcement, we will make a ceramic green body which would be acting as a preform. So basically a preform is ready. Then we make a growth barrier on top of the preform so that we can control the growth of the matrix inside the preform. A growth barrier is put on top of the preform, and once the growth barrier is put, the molten metal is oxidized, or directed oxidation takes place of the molten metal, and the products that are formed are acting as the matrix material for the preform. So we will get a composite material in which we have a matrix also and the reinforcement also. The reinforcement is in the form of a preform, and the matrix is being grown because of the directed metal oxidation. So this is a very simple summary or very simple representation of the process. Again on your screen you can just have a look: preform fabrication, matrix growth, and finally the final product. Matrix growth is the most important part of the whole process, or the heart of the process, because here only we are combining the two things together. As I have already discussed in the very beginning of today's lecture, when we started this lecture, I have just introduced the, we can say, concept of composite once again, because there may be an audience which is only interested in this particular lecture, that a composite is basically a combination of a reinforcement and a matrix phase, and in combination they give the properties which are not attainable with any of the individual constituents. So basically in all the processes which are used for processing of composites, we have to blend, or we have to combine the two phases, that is the reinforcement and the matrix phase, together. In this particular case of directed metal oxidation, this is the reinforcement, and the matrix is being grown because of the reaction, that is the directed metal oxidation. So this is the important phase where we have the reinforcement in the form of a preform, and the matrix is growing inside the preform to make a dense composite product. So basically the growth of the matrix phase is an important point, and here we have to control the process properly so that we get a good quality composite product. Otherwise there would be some kind of defects or some kind of problem areas that have to be addressed at later stages. So that we will discuss in the subsequent slides, that what are the various disadvantages or limitations of the process. But yes, this process has been found to be suitable for fabricating ceramic matrix composite materials. Now let us come to the advantages of the process. So we can see there are certain advantages. The process is relatively a low cost process because near net shapes of the end product is possible. Now let us see, there are 2-3 important points in this particular advantage. First important point is that it is a low cost process. So we have seen some of the other processes for ceramic matrix composites or for processing of ceramic matrix composites which are high cost intensive processes, because the kind of or the mechanism involved is a high cost mechanism, or it involves sophisticated instrumentation. But in this particular case, no sophisticated instrumentation is required, therefore this is a simple low cost process. So the process is relatively a low cost process, that is one important point. And why it is low cost, there can be other point. One is that the instrumentation or the infrastructure required for this process is not very costly, as I have already highlighted. The second point why it is low cost is because it can be used for near net shapes of the end product. Now what do we mean by the near net? Near net means the exact shape of the final product. Near net means the net shape near to the net shape product we can make by this process. So basically it is a near net manufacturing or near net processing technique. Why? Because in this we are creating the preform as the first step of the process. If you remember the steps involved in this process, we have seen the very first step involved is the fabrication of the preform. So the preform we can make in the shape of the final product or the end product that is desired. So as per the design requirements, we have a shape of the product, and the preform we can create according to the shape of the product. And once the shape of the product has been made, then we can grow the matrix inside that shape and directly get the final product, which is not possible in the some of the other processes which are used for processing of ceramic matrix composites. So therefore this process can be used to make near net products, and therefore the additional processes or the post processing techniques may not be required in terms of machining or rolling or giving it a shape at a later stage after forming a bulk of the material. Sometimes we trim it, remove the material and form it to give a desired shape. So all those secondary processing or post processing processes are eliminated when we are able to generate a near net product, and this particular process has the advantage of producing a near net product. So therefore this is low cost process and least expensive in terms of producing the products, because it is able to generate the near net products, and secondary processing or post processing of composites need not be done if the product has been produced by the directed metal oxidation process. Now the second advantage is that good mechanical properties such as strength and toughness can be obtained. We will see that from where the toughness is coming into picture, because the toughness is related to, is one of the important parameters in case of the ceramics. So we need certain amount of toughness in case of ceramic product, and specifically in ceramic matrix composite product. So how the toughness is coming into picture, that we will see. So but one important point to note here is that we get good mechanical properties in case of directed metal oxidation process for processing of ceramic matrix composites. Now what are the disadvantages of this process? There are salient disadvantages, some important disadvantages also. Control of the reaction is very difficult, as the name of the process suggests, directed metal oxidation. So here the reaction is taking place, or the oxidation of the metal is taking place at a elevated temperature. So the control of reaction is very difficult. That is one important disadvantage, because the reaction is acting as, we can say, one of the important sources, or is the important source for the formation of the matrix inside the preform. And if we are not able to control the reaction properly, the formation of the matrix inside the preform or the growth of the matrix inside the preform would not be optimal, or would not be as per the desired requirements or as per the desired specifications, and therefore the final composite product that we will get may not have the properties for which it has been processed or designed. Therefore the control of the reaction is very important, and if we are able to control the reaction properly, we will be able to get a very dense composite product, a composite product which has very good mechanical properties, which has got good toughness and can be used for a variety of engineering applications. So the important point, as I have already told, that there are basically 3 steps involved in the process. First step is the formation of the preform, and second step is the growth of the matrix inside the preform, and the second step is the most important step in the process, because here we have to control the process in the most optimal manner, otherwise we will not get the product according to our requirement. So the important point to control is the reaction, because reaction is the, we can say, backbone of the formation of the matrix inside the reinforcing preform, or the reinforcement in the form of the preform. So the growth of the matrix is important, and that growth of matrix depends upon the reaction, and if the reaction is not controlled properly, we may not get a very good composite product. So again and again the emphasis is on the growth of the matrix inside the fibrous preform. So this is important point to control the reaction properly. Second important disadvantage is that all the ceramic matrix cannot be processed by this process. So different types of ceramic matrix cannot be processed. Maybe we can have a selected matrix materials that can be processed by this process. The technique is very challenging for manufacturing large complex parts. So, if we have a small part, we can grow the matrix in a particular direction inside the fibrous reinforcement, but if we have a very large part, sometimes we may not be able to have a uniform distribution of the matrix material inside the preform, and the quality of the product that we get may not be that good. So, the technique is challenging. It cannot be said that it is impossible, but it is challenging. There are different types of operating variables that need to be controlled if the size of the product is large. So, this particular technique is very challenging for processing of large complex parts. So, one is large, another is complex. So, if the geometry of the preform is very complicated, in that case also sometimes we may not be able to grow the matrix properly inside the preform. So, in those cases also we may not get a uniform density of the product, or we may not get the uniform properties all around the bulk of the product. So, basically there are challenges also or disadvantages also related to the directed metal oxidation process. Just to highlight the challenges because, or the highlight the disadvantages, because this is important from the application point of view, because when we are making a product and there are few challenges or disadvantages, those have to be overcome in order to make a product of very high quality. So, one is to control the reaction properly, that is the directed metal oxidation. Second is that all the materials cannot be processed by this process, and last one, that this technique having a challenge if the shape of the product is very complex, and if the size of the product or the ceramic matrix composite product is very large. So, these are important points to be taken care of. These are the important limitations of directed metal oxidation process. Now, let us come to the applications of this process. The applications are, we can see, let me first read all the applications. This is used for making heat exchangers, radiant burner tubes, flame tubes, high temperature furnace parts, high temperature gas turbine engine components. So, basically you can see most of the application, rather I should say all of the applications are related to high temperature applications. Heat exchanger, where the temperature would be very high. Radiant burner tubes, wherever the burner word comes, the temperature is ought to be high. Flame tubes, flame, automatically the temperature is high. High temperature furnace parts, high temperature gas turbine engine components. So, this particular slide emphasizes the application of the ceramic matrix composites. In other processes also that we have seen, like powder processing, chemical vapor infiltration, slurry impregnation and liquid infiltration, all these processes make the parts or the ceramic matrix composites part, and all these parts are useful for high temperature applications. That is one of the, we can say, important application areas for components made by ceramic parts or ceramic composite products. So, basically we can see on this particular slide the important emphasis or highlight of putting this slide in this presentation is that whatever parts or whatever applications we are suggesting for the composite products made by within the ceramic matrix or the ceramic matrix composite products would certainly find application in high temperature applications or elevated temperature applications. So, whatever product is designed, it has to be designed keeping in mind the final requirement or the final application of that particular product, and most of the products of ceramic matrix composites are finding applications in high temperature regions. So, basically we can say that whatever processes we have covered are focusing on the high temperature applications only, and therefore the processes have to be understood with a manner that the product that would be made by these processes would be subjected to elevated temperature, and therefore the process induced properties should be such that they are able to withstand the high temperature applications, because during the processing also some properties would get changed. There would be an interface that would be developing between the matrix and the reinforcement. What should be the strength of that interfacial bond between the matrix and the reinforcement? What are the type of stresses being developed during the processing, which would later on act as, we can say, failure for under the different types of application. So processing induced properties are important to understand when the product would be used for specific applications. But our focus primarily in this particular module is to understand the fundamental aspects, that how the raw materials, that is the ceramic matrices and the reinforcements, are combined together to make a composite product. So we have been able to discuss number of processes. Now we will see the last process for processing of ceramic matrix composites, that is the sol gel processing. We will just see the fundamental of this process or the basic process mechanism and move on to the last part of this module, that is the post processing of ceramic matrix composites. So let us now quickly see the basic mechanism of the sol gel processing technique. In this particular technique, very fine particle size or very fine particles are used as the, we can say, the matrix material. We can have a preform, and in that preform we will impregnate or we will infiltrate the matrix material, which would finally under the, we can say, temperature would form a final or a regular matrix, and we will get a composite product. So firstly from the sol we will get a gel, and the gel would finally take the shape of the matrix on solidification. So let us see with the help of a diagram typical steps involved in the sol gel processing. Very simply we have been able to represent. First is the pouring, that is pour the sol over the preform. Drawing, desired density if it has been achieved. If it has been achieved, then we will go for the next step, that is firing. If it has not been achieved, multiple infiltration and drawing. So basically this process is quite similar to the liquid infiltration process that we have already discussed in our previous lectures in this module only, that is module 6 on ceramic matrix composite. So in liquid infiltration process also we are infiltrating a slurry or a liquid into the preform. The preform is the reinforcement, and the liquid that we are infiltrating into the preform acts as the matrix material. And this process is similar to the resin transfer molding process that we have already discussed in the previous module on the processing of polymer matrix composite. So in this process also the pouring over the sol, pouring of the sol over the preform, that is the first step, and then the drying takes place, and finally if the desired density has been got, we will stop and finally go for the next step, and if the desired density has not been got, then the multiple infiltrations would be done. So this is a sol gel process. The gel would finally solidify to give us the matrix inside the preform. Now what are the advantages of this process, sol gel? Because I have already told we are not discussing this process in detail because it is quite similar in principle to the liquid infiltration process, where the preform is there and the liquid infiltrant is there. We have understood it with the help of a diagram. There is a piston, the piston presses the liquid infiltrant, the infiltrant goes and fills the open spaces inside the preform and forms the matrix. So here also if you see the steps involved in the process, the major mechanism or the basic mechanism is same, but there are process details which are different in case of sol gel, because I have told the particle size is very small in case of sol gel process, and there are other process details which are different, but the basic mechanism is similar. So what are the advantages of this process? Low processing temperatures results in low damage to the preform. So preform, if it is a complete network of fibers, so if high temperatures are there, there can be damage that may take place to the preform, but in this particular case low processing temperatures are involved, therefore minimal damage to the preform takes place. Next is the ease of fabrication of complex shapes. So this particular process can also be used for processing of complex shapes. As we have seen in our previous process today, that is directed metal oxidation, we can give a direct shape or a near net shape to the preform and then grow the matrix into the preform to get a final product. So it mitigate or limits the post processing of the final product that has been formed. So in summary, we can say any product which has been made by the directed metal oxidation would require minimum post processing processes because it is made to a near net shape. Here also, in case of sol gel processing, there are two major advantages. Advantage number one is the processing temperatures are low, and therefore the damage to the preform is also low, and which is very important, because in the slide that we have seen related to the applications of the ceramic matrix composite product, if you remember, we have seen most of the applications are high temperature applications, and there I have told that the processing related properties should not affect the performance of the ceramic matrix composite product in service, which means this important point is related to that sentence which I have emphasized again and again, because if the fibers would get damaged or the reinforcement would get damaged during the processing, then when this product with damaged preform or damaged reinforcement would be used in actual application, there is ought to be a deterioration in the performance of the product. So therefore, in this particular process, that is sol gel processing, the temperatures involved are less, and therefore less damage to the preform takes place, and finally the final product that we will get would be of good quality, and it would be able to perform its desired function reliably over a period of time. And if we induce, or if process related we can say defects are there, or process related deterioration of the properties takes place during the processing, then the product that we will get may not be able to perform its desired function reliably at a later stage or over a period of time. Therefore, we have to process the materials in such a way so that they are able to perform their function properly. So we have to minimize the damage to the constituents during the processing. And then another advantage is that this particular process can be used for complex parts. Then there are certain disadvantages also which have to be taken care of, that is high shrinkage results in matrix cracking. This is also related to the performance of the product at a later stage. If matrix cracking takes place, the product may not be of good quality. Why matrix cracking is taking place? Because of the high shrinkage that takes place during this process. So this is one particular advantage, high shrinkage leading to the matrix cracking. Next is low yield, which requires repeated infiltrations to increase the density of the matrix. As we have seen in the 3 or 4 steps which were there in the process, that if we are not able to generate the adequate density, then we have to do multiple infiltrations, and therefore this process is a slow process. So the low yield, which requires repeated infiltration or multiple infiltrations in order to increase the density of the matrix, and if we are not able to make a dense matrix, the final product may not be of the desired mechanical properties. So therefore, in many cases multiple infiltrations may be required in order to generate a matrix of adequate density. So these are some of the important disadvantages related to the sol gel processing technique of ceramic matrix composites. Now coming on to the major topic for today's lecture, that is the post processing of ceramic composites. So 4 major class of post processing techniques are there. Let me name all the 4. First one is the mechanical, second one is impregnation or sealing, third one is thermal, fourth one is irradiation. So before going to the examples of these post processing techniques, let us first focus on the need of the post processing when we have already processed the composite part. If you see, by now we have discussed at least 4 or 5 different processing techniques for ceramic matrix composites. To name them, we have seen powder processing, we have seen CVI process, we have seen slurry impregnation process, we have seen liquid infiltration process, we have seen directed metal oxidations, and the sol gel processing. So all these techniques would give us a ceramic matrix composite product. Once we have got that product, in order to make it suitable for a specific engineering application, we may require to do some post processing on that product which has been made by any of the processes which I have just outlined. So post processing is to give a specific edge to that product for a specific application. But in many cases we have to go for post processing, but in some of the cases, as we have seen in case of the directed metal oxidation, we get a preform of a desired shape in which the matrix grows and a near net product is made. So if when the near net product has been made, which reduces the application of post processing on that product, because already we are getting a near net product. But in that case also, if there is a specific application for which a product has been made by the directed metal oxidation process, we may still go for some of or any of these processes which are there on your screen. So in case of directed metal oxidation product also, or the product of or the ceramic matrix composite which has been made by the directed metal oxidation process, in that case also we may sometimes go for post processing, depending upon the final requirements of the product for which the product has been designed. So now we will see one by one that what are the various types of post processing techniques which are used for ceramic matrix composites. Mechanical. These are also known as finishing processes. These includes rolling, squeezing, grinding and polishing. So once a ceramic matrix composite product has been made, in order to give it a suitable finish, in order to give it a sometime a required shape, we may go for mechanical type of post processing. So the some of the examples of the processes that fall under the mechanical type of post processing are squeezing, grinding, polishing and rolling. So these are 4 type of processes that fall under the mechanical post processing technique for ceramic matrix composites. Next one is the impregnation and sealing. This process involves impregnation of lubricants or sealants into the pores of the component in order to improve their performance. So that this is second type of the post processing technique, that is impregnation or sealing. In this particular case, all of us know that ceramic matrix composites have certain degree of porosity, and in those pores in many cases we may like to impregnate the lubricants or the sealants in order to improve the performance of the ceramic matrix composite product. So first important post processing technique is the mechanical post processing, in which we are finishing the final product which has been made by any of the processing techniques for ceramic matrix composite, and sometimes we may do rolling or squeezing also, and finally grinding and polishing in order to improve the surface finish. So mechanical post processing can be done. Then impregnation and sealing are the other post processing techniques which are used. Example has already been given, the pores can be filled or impregnated with oils or sealants or lubricants in order to improve the performance of the product. Then we can see the other type of processes like the thermal processes of post processing. These are basically heat treatment processes and include laser melting, hot isostatic pressing, high intensity pulsed ion beam processing or heating, conventional furnace heating. So sometimes we may require to heat the ceramic matrix composite product in order to achieve certain important characteristics or properties which are required for application of this particular product in certain specific domain. So we have seen there are till now 3 types of post processing techniques, that is first one is mechanical, second one is impregnation or sealing, third one is thermal. So thermal also may be required depending upon a specific application. As we have seen, the applications of the ceramic matrix composite product in today's lecture, all the applications were related to the high temperature applications. So therefore the thermal post processing of the ceramic matrix composite product become imperative or becomes necessary in order to subject them to a specific working environment. So thermal post processing is also important. The examples of thermal post processing are given on your screen. You can see it may involve heat treatment, it may heat treatment processes such as laser melting, hot isostatic processing. So they are basically heat treatment process and includes laser melting, hot isostatic pressing. Then we can have conventional furnace heating and high intensity pulsed ion beam heating. So basically we are heating the CMC product to get certain desired properties so that it is applicable for a certain application spectrum. So finally we come to the last post processing technique, that is irradiation. This technique is especially employed for ceramic composites. This involves refinement of microstructure through the controlled microwave irradiation. So microwave also is a source of heat. So in case of microwave irradiation, we are able to improve the properties or the microstructure of many ceramic composite products. So irradiation is an important technique and which is specifically applied to the ceramic matrix composite products in order to improve certain characteristics of the ceramic matrix composites. So with this we come to the end of our module 6. In our final module, that is module number 7, our focus would be on the secondary processing techniques for various types of non-metallic materials, in which we may see the machining of polymer matrix composite, joining of polymer matrix composites, and in many cases some post processing techniques related to the ceramic products also. So today we are ending our discussion in module 6 on the post processing of ceramic matrix composite products, and finally we will start our discussion in module 7 with the secondary processing techniques for different types of materials. So in today's lecture we have seen the two important techniques for processing of ceramic matrix composites, that is the directed metal oxidation and the sol gel processing, but very few fundamental aspects of sol gel processing only we have seen, and also we have seen 4 important post processing treatments that are given to the ceramic matrix composite products in order to give them certain specific characteristics and properties to make them applicable in certain defined application areas. So with this we come to the end of module number 6. Module number 6 has focused on the ceramic matrix composites. We have focused on the mechanical properties of the ceramic matrix composite, the fundamental aspects of the ceramic matrix composite, and finally the processing aspects of the ceramic matrix composite. And we have seen different processes which are used for processing of ceramic matrix composites, and in today's lecture we have seen some important post processing treatments that are given to the ceramic matrix composites in order to improve their application spectrum. Thank you.